In this lecture, we'll continue our discussion on solid state physics. Okay, so before moving on towards understanding the reciprocal lattice and the Miller indices, we have to do some more work. And one work is defining the lattice vectors for various cubic lattices. For example, take an example of cubic lattice, simple cubic lattice. Okay, so what we'll do here? Here I have drawn a cubic lattice. Okay, so as you know that there are atoms at these corners, so this is always there, so I'm not drawing it again and again. Okay, let me draw it. So there are atoms on each corner, and the x, y, z axis are specified according to the diagram. Agreed? Now, so what are the three vectors, the lattice vectors that define this cubic lattice? As we discussed earlier, there will be three vectors. A, this vector is also A in the y direction. Since it's a cubic, all will be same, and in the z direction again we have the same vector, that is A. These three vectors, they are the most important lattice vector, okay, that govern the translation. For example, as I've already said, that using these three vectors you can keep on constructing this cube. Okay, you will be having a cube in all the directions. For example, you can have a cube here just by using this translation vector, and you can calculate the and you can form the entire lattice, entire cubic lattice, as we have discussed earlier. Okay, so what are we discussing here is how to write the lattice vector in vectorial form or in the component form also. You see, the x component has ax, the y has ay, and z has az. Now if I take another vector, if I take another object and I put it here, an atom, this becomes a body centered cubic lattice. Okay, so in a body centered cubic lattice, I cannot have a1, a2, and a3 as my basic lattice vector. I will have something different. Let us see. Yes, this is the body centered lattice. Okay, as you can see in the body centered lattice, it is clear that the a1, a2, and a3 are in other direction. For example, the a2, a1 and a2 are same, okay, but a3 is different. Since it's a cube and it is related to this simple cube, so I can state that my a1 is nothing but a in the x direction. Okay, because this body centered cube was made by using this simple cubic lattice. Okay, similarly I can state my a2, which is similar to ax, as I said, because this body centered lattice is made from the simple cubic lattice. And then when the time comes to define a3, okay, now a3 has to be understood. Now a3 is a vector in this direction. Okay, a3 is a vector. Now a3 is a vector that represents the body centered atom. Now you know the body centered atom is exactly at the center of the entire cube. So when it is at the center of the cube, if you draw a normal, you see the red line, okay, and then you take two normals from here on the x-axis and a normal to here on the y-axis, then this part will be a by 2 actually. Okay, and this part, the red line here, is also a by 2, and the height is also a by 2. So you see the a3 vector has three components. Okay, in the x direction it has component a by 2, in the y direction it has component a by 2, and in z direction it has component a by 2. So it has three components because a3 is not aligned in a unique direction like a1 and a2. A1 was in x direction, a2 was in y direction. Oh, let me make it. So this was the y direction. Okay, so a3 is neither in x nor in y, but somewhere in between. Okay, in the middle. So the a3 vector can be written as, since the magnitude in each side is a by 2, so a by 2 is as it is. Oh, let me write it in another form. Wait. So we have an a by 2 in x direction. So a3 has a component a by 2 in the x direction. Now a3 has another component a by 2 in the y direction, as I have already mentioned in the diagram. And a3 has another component a by 2 in the z direction. That is clear from the diagram. Okay, so this is how the this is the component form of the lattice vector of the body centered cell. So this was the body centered cubic lattice. Okay, the BCC. Similarly, we can also discuss about the lattice vectors in case of face centered cubic lattice, and we'll try to see how the vectors will have the components. Let us see. So here I have a face centered cubic lattice, and as I said, this face centered cubic lattice is made from the simple cubic lattice. I mean to say that this length is as usual a, and this length is also a. I mean the height, breadth, and the length, everything is a. Okay, so I'm deleting that part. Now the a1, a2, and a3, they are all in different direction. Neither a1 is in a particular x or y direction, neither a2, neither a3, but a clear understanding can be obtained from here. Now look at this face centered atom here. This is exactly at the middle. So we can say that this part is actually a by 2. So this is exactly at the middle. So the a2 has two components, one in the x direction, that is a by 2 x cap, and this a2 will have another component in the y, in the z direction. Let me write to see, here I've drawn. Yes, so this part is the z direction, so this will be a by 2 in the z cap. So these are the components of the a2. So you can see from here the a2 has a by 2 in the z direction and a by 2 in the x direction. Now what about the a1, a3? So you know that this particular atom is also on one side of the face, that is at the bottom face, and this part is gonna be a by 2 y cap. Okay, so now a3 has two components, one is a by 2 x cap and another is a by 2 y cap. So we can see that a3 has a by 2 x cap and a by 2 y cap. Now how about we are left with a1. Now a1 is also on the face. Okay, a1 is also on the face, and by using the same argument you can prove that a1 is a by 2 y cap plus z cap. So it has a component a by 2 in the y cap direction and another component a by 2 in the z cap direction. So we see that how we can write the lattice vectors in the form of components for various cubic lattices. Agreed? But the most important assumption was that this face centered cubic lattice was made from a simple cubic lattice and all the sides had total length of a. So all the sides have length a, the length, breadth, and height, everything had the length of a. And then in terms of a, we wrote down all the three lattice vectors of face centered lattices, that is a1, a2, and a3. Okay, now there is something very much interesting about these vectors. These vectors, they can also be written in a different form. Okay, you can choose your origin, and the value and the structure of these vectors can change according to origin. For example, let me give an example of body centered. You see, Here you see a body centered cubic lattice. Agreed? So you see a body centered cubic lattice. Now, I already discussed how A1 is AX, A2 is AY, and A3 is this. Already discussed. But you can make a slight change in origin that has been not shown in the diagram. But just assume it. You can make a slight change in origin, and your A1, A2, and A3 is gonna look different. Okay. So depending on the origin and depending on the direction of lattice vectors, the components can be different. Now, why are we doing this? Because sometimes in the question you might be given a particular form of body centered cubic lattice and you will be given its lattice vector. Okay, so here the lattice vector, for example, is given as this, the one in the blue color. And if you are given this with these three lattice vectors and you are asked what will be the reciprocal lattice vector, then there is a particular form of calculation that we'll do in the lecture in future, now in further lecture. But this is why this is being taught. Okay, but we have a bigger motive behind this that we'll understand later on. But keep this in mind and let me continue. So now we'll return to our reciprocal lattice. Here you will get a small review about reciprocal lattice, not a full review. Okay, but you will get a hint what reciprocal lattice actually is. But in the next lecture only you will get the hint why we invented the reciprocal lattice vector. But in this lecture you will get a hint about only reciprocal lattice vector, what they actually are. Okay, in short, reciprocal lattice vectors are the vectors in the Fourier space. This is the definition. Okay, even if you don't understand this, we'll continue, you'll understand. So remember Fourier series. Yeah, any function f of x, if it is a periodic function and has a period of 2l, then what we do is we write a Fourier series like this. Agreed? However, just let me mention one more point. Okay, so this is the Fourier series that is written. However, if the period is, so here the period is of the function is 2l. Remember the period is 2l. But if the function f of x will have a period l, say f of x has a period l, then there will be some changes. The changes are, okay, if the period of this function f of x becomes l, then all you have to do is put a factor of 2 here, put a factor of 2 here, and put a factor of 2. It's very easy. Okay, it's very easy. So you put a factor of 2 here only when the period is l. Okay, and you don't have this factor 2 here when the period is 2l, but we'll deal with the period l. So this is the general definition of Fourier series that you have already learned during your BSc classes. So while defining it, let's continue. It's because, consider you have a crystal. What is the most important part of a crystal? So what is the most important property of a crystal? The most important property of a crystal is that its property, whether it's electrical properties or say electron density, so the internal properties, they are periodic. If the crystal is periodic, obviously a property, say its electron density, it's going to be periodic because it's an internal structure of that crystal. So let us continue. So in the diagram you see two things. So consider this is a 2D lattice and consider this is a 1D lattice. Okay, the moment I use the word crystal, what I mean to say is there is something periodic. For example, if this is a crystal, so this is a, say, 1D crystal. Okay, although in our real world you see 2D crystals, just assume this is a 1D crystal. So what is the most basic property of 1D crystal? What should be happening? What should be happening is that if you have at this point a particular electron charge density, say n of x, so this is an electron charge density. Okay, then if you make a particular translation from this part of the this part of the crystal to this part of the crystal, say you made a translation of T. So when you reach this part of the crystal, should you expect a different electron density or the same electron density? Because here we have an atom, 1D atom, and here we also have an atom. Since the same atom is getting repeated, of course I must have the electron density here as x, n of x, because there shouldn't be any change in the electron density. If there is a change in electron density, then there will be a change in the type of atom here, but I'm not considering that. So I'm considering the same atoms are being placed, and if the same atoms are being placed, then what is the most important mathematical property? The mathematical property of the electron charge density is that if I make a particular translation, say if I go from a particular n equals to x, so say this is x, okay, and say what is this point? This is x plus t, because I have made a particular translation. Okay, then my n of x plus t, that is the electron charge density at point x plus t, must be same as the electron charge density at point x. This is a very logical thing to consider in a crystal. Okay, so what we see is that the electron charge density, so what we expect is that the electron charge density here is given as n of x, and this electron charge density is a periodic function that is given as here. It has to be periodic. There is no way it cannot be periodic, or else the very definition of the crystal has no use. Okay, the very definition of the crystal dictates that there is a periodicity in the crystal, or there is a periodicity in the lattice, and those periodicity occur when you move by the basic lattice factor. For example, consider here the movement is being a, so consider here the movement is a. Okay, then what should I say? I should say that n at any x is same as, if I move a distance forward, then the electron charge density should be same, then the electron charge density should be same. So here I can write x plus a. Now if a, what is a? A is the most basic lattice vector. Okay, so what is t? T can be anything. So t can be even 3a. Okay, t can be even 3a, 4a, 5a, or whatever. The translation can be anything. So if you move, look at the blue line. So if you are at this position, here you are saying that the electron charge density is x. Then if you move from this point and if you reach this point, okay, through a translation t dash, okay, then what should happen? What should have happened is that the electron charge density at this position, which is n of x plus t dash, should be same as the electron charge density that is found earlier. Okay, this is the basic definition of the electron charge density. So the very structure of the crystal dictates that there is something periodic. So these type of things like the electron charge density and all the things will be periodic. Similarly, consider 2D case. In a 2D case, consider all these points, they contain atom. Okay, so every intersection you see, they contain an atom. So I'm not drawing everything. Okay, they contain an atom. So if this is a crystal lattice, then again if I calculate a particular charge density at this point, okay, and I make certain translation and I reach this point, here what should I expect? If I have made some translation by t, then the charge density at this point is mathematically given as x plus t. Though it is mathematically given as x plus t, physically they should be same. Why would the charge density be different? Because this is a crystal, and this crystal is just a repetition of this particular lattice, this particular square lattice. So if it is a repetition of this lattice, then whatever I find in this lattice, I should find it everywhere. Agreed? So this is the main point. So the main point is any property will be periodic in your crystal lattice. Agreed? So if these type of properties are periodic, then I can easily expand them in Fourier series. So let me write the Fourier series expansion of electron density n of x. This is the electron density. Yep, this one. Okay, so this was in 1D. Okay, now you can see that n of x has been represented in Fourier expansion, and you can easily check that if you do n of x plus a, I mean a translation of a, then you will find the same electron density. So you will get n of x. So this is the requirement that the crystal lattice has asked for, because the very definition of crystal lattice says that things should be periodic. So this is the 1D case. Now if you can concentrate on the part 2 pi p by a, okay, these 2 pi p by a is actually the points on the Fourier space that represents the periodicity. So for example, in your real space you take coordinate as x and the lattice vector as a, that defines the periodicity. When you go to Fourier space, the periodicity is defined by points like 2 pi, p is an integer, divided by a. So there has been a change from so a was like, a has a dimension of length, okay, and there has been a change to dimension of 1 by length. So there has been something in the Fourier space. You are actually dealing with objects that has dimension 1 by length. So this is the 1D case. Okay, so how about the 3D case? So what happens in the 3D case? So before going into the 3D case, let me write the complex form of n of x. Okay, that is the 1D. So let me write the complex form. So here I have written the complex form of the n of x. So this is nothing but again a Fourier series in complex form. From here also you can check that if I transfer this x to x plus a, okay, then also my n of x remains same, because you can use the property that e to the power, okay, I into 2 pi and any integer p gives a value of 1. So this is the property that you can use. So this is the Fourier expansion in complex form. So now let us deal with 3D. So how about take a 3D crystal, and in 3D crystal you want your n of x, which is the electron charge density, to be invariant under any translation in 3D. Okay, so in 3D the translation is given by t, but the form of t will be different. For example, in 1D the translation was given by this, so it has only 3a because a was the only parameter. In 2D you can use, so remember in 2D you will have two lattice vectors, so one will be a1 and another lattice vector will be a2. So any translation in 2D can be given as a combination of, say, any integer u1 with a vector a1, okay, and any integer u2 with a vector a2. Okay, so this is your 2D case. So what will be the translation in 3D? So when you go from 2D to 3D, so there is another vector that is a3, and as a result of which the translation vector will have another vector that is u3 a3. Okay, now please remember these are all vectors, these are all vectors. Okay, so under this translation t, so this translation t here represents this translation t. So under this translation t I want my electron density n of x to be invariant. Now in 3D I can write again this electron density n of x in complex Fourier series because n of x is periodic. So let me write, okay, check out. So this is the complex Fourier series of the electron density in 3D. So notice that in case of in place of x I have used r, because in 3D you will have three components x, y and z. Agreed? Now this g is something that I have no idea. Okay, I want to find g. So what is the use of finding g anyway? Okay, so there is a reason. In 1D case, you know that any translation t will be in the form of a, and you also found the points in the reciprocal space. In the reciprocal space, what was the point? 2 pi p is an integer divided by the reciprocal vector a. Agreed? So this was the point in Fourier space. I mean 2 pi p, if you can look at this Fourier series in complex 1D, so you can see that the reciprocal point was 2 pi p by a. I mean the Fourier point. But the Fourier point in 3D here is unknown to me. All I know that I have an electron density n of r, and I can write the electron density of n of r as a Fourier function or as a Fourier expansion. And one more data that I have is n of r has to be periodic. It means n, which is a function of r, will be same even if I go from r using a translation vector to any other distance or any other place in the crystal. There will be same electron density. So any translation t should give me the same electron density in 3D. So I have these two information with me in 3D case. Okay, and I need to find what will be the Fourier coefficient, Fourier points in 3D. So that I need to find. So g is something that I don't know. So what I know, as I said earlier, I know this equation and I know this equation, and I have no more idea, and I want to find g. Okay, so let us see how to find g. So what do I have? So I know that this is something that I have. So in the form of equation, what will it become? I should have e to the power I g dot r. Okay, this thing must be same as if I make a translation. That is, if I make a translation by using a translation vector t. So if I go from r, okay, to some place by using a translation vector t. Agreed? So this is also vector. Now this thing should be same. So remember, I am finding g. Okay, g is something I have no idea. I have no idea what the Fourier points in g will look. All I have idea is r and my t. Now can you tell me what my t will look like? Okay, so before writing t, just let me write one more step here. Okay, that step is written. Now please see carefully. You see that this part has to be same as this part. Only then the n of r will be same as n of r plus t. Okay. Now for this part to be same as this part should become a 1. So this part should go to what? Should go to 1. So what this part is saying, that g is something I don't know, but t is something I know. So e to the power igt should be 1. I mean that, what is t? So I can write t here as, this is my t. Okay, so this is a translation in real space. So when I say real space, I mean the crystal in my 3D space. I'm not talking about Fourier space. Now consider, let me assume g. So let me assume g can also be written in this above style, but the vectors will be different, and those vectors will represent the Fourier vectors. This is my g. Okay, so this b1, b2, b3 are something that I don't know. The only information I have is this part should be 1. This part should go to 1. So let us plot these two values into this equation, and let us see what do we get. So e to the power igt can be written as, so what I've done here is I have just put the value of g here, and I put the value of t here. You can see the color black and yellow. So what do I get? So what I get is, I'm writing it here. So I've written it here. Now you'd ask me, where is A1 and B1? Okay, the reason is the following. So I started with a electron density in 3D and I have no idea what the Fourier point will look like. My electron density had to satisfy one more condition, that it is periodic and in translation T. My translation in T was known to be this. This is my translation in T. And G, I have assumed an arbitrary value of G such that G dot T will give me a scalar value. So obviously G should be of same form as that of T. Now, not only that, I also want my e to the power IGT as 1. So if I want my e to the power IGT as 1, then remember this formula. What you have to do is e to the power I into 2 pi, any integer is gonna give me 1. So e to the power I 2 pi, this is nothing but integer, because multiplication of integer will give me an integer. So this is 1. So to make this part as 1, what game I have to play? I have to assume that somehow this B1 and A1, when they are getting multiplied, I am getting a value of 1. Or more precisely, I can say, or I can make the condition that any BI, when it is getting multiplied or with the dot product with AJ, okay, should fetch me an answer of delta I j. So fetch me an answer of delta ij, or I can make it more precise, delta ij into 2, because I have included a 2 pi above. So this is the definition that I need to impose to get 1. This is the definition I need to impose to get the 1 here, that I am marking with the yellow line. Okay, so BI's are the vectors in the Fourier space and AJ are the vectors in the real space. By real space, I mean our space where we are actually seeing the real crystals. Now I need to guess what will be the values of this B in terms of A, such that the value, the dot product of any B and A will give me a 2 pi. Agreed? So my guesswork will lead me to the following values of B. This is my guesswork. So you can easily check that only if B is written in this form, then I can satisfy this equation. Okay, let us see what happens when I dot product B1 with A. So when I dot product, so B1 with A1, so what do I get? The 2 pi is as it is. Okay, in the upward position I get A1 dot A2 cross A3. Below I have A1 dot A2 cross A3. They will get cancelled and I'm left with only this. It's a straightforward calculation. Agreed? So only if my B1 is in these forms, only if my B's are in these forms with A's, only then I am able to satisfy this condition. Okay, this B1, B2 and B3 are called as reciprocal lattice vectors because they span the reciprocal lattice. Like the A1, A2, A3, they span the real crystal. Okay, remember the first lecture when I used the A1 and A2 to span the entire crystal, entire 2D crystal. Similarly, A1, A2, A3 will span the entire 3D real crystal. Whereas B1, B2 and B3 are the vectors that will span a hypothetical or imaginary Fourier crystal related to the real crystal. So any real crystal which can be spanned by using three lattice vectors A1, A2, A3 has a reciprocal reciprocal space. Okay, has a reciprocal space where the crystal will have a brother, something like a brother, a reciprocal mirror, a mirror image, not exactly mirror but in a different space. And that crystal, when it is in the reciprocal space, that crystal will have a different form, and it will be spanned by the vectors b1, b2 and b3. So this is the idea behind formulation of reciprocal vectors. But again, the question is why do we have the reciprocal vectors in the first case? What need did we find that we to define this type of vectors? Okay, so I'll give you a hint of why we were so interested to find this reciprocal vectors instead of using the real vectors. You see, there is something called as diffraction. Okay, we'll discuss in the next lecture, but I'll give you a short review. Okay, before going further, let me describe you this graph. This was the 1D graph that I discussed in the first place, telling you that this is the electron charge density. You see the electron charge density is getting repeated this side and this side, and you see the interval of repetition is 2 pi by a, so that is n pi by a. Okay, so these are the space. This is the 4 points in the Fourier space. Okay, and look at the interesting thing about Fourier space. It is 1 by length. Agreed, it is 1 by length. Okay, just remember this very important point. This is 1 by length. Okay, so let us continue. So what did we learn? We learned that there are crystals in real space, and the real space crystal is called as crystal lattice, and we can study the same crystal lattice by taking and making another crystal lattice in reciprocal space. Okay, so in reciprocal space, when we make the crystal lattice, instead of using the vectors a1, a2 and a3, we use the vectors b1, b2 and b3, and the a and b's are related to each other by this formula. Agreed. Now this is something different. So question is, why do we go from, so we wanted to do something, and to do something we went from crystal lattice, that is a real lattice, and we said that let us work everything in reciprocal lattice. Okay, so this is like a kind of mapping. If I give you a good example, then I would say, so consider you have a real world with trees, grass, buildings, everything, etc., and you want to do some experiment in the real world. Agreed, but you planned that instead of doing the experiment in the real world, why don't I make the real world inside the computer? So when you take the real world inside the computer, then instead of using the objects in the real world, you use programs in the computer. For example, people make modeling of galaxies. Okay, you have a galaxy outside, you cannot do any experiment with the galaxies outside, so what you do, you make galaxies inside the computer. The galaxies outside are made up of particles and atoms and molecules and elements of various atomic number and etc., but your galaxy inside the computer is made up of just programs. Agreed. So what is the use of going from real to a model in computer? Because it helps you a lot, it makes things simple. Instead of doing the real experiment, what you do is you first do the experiment inside the simulation. If the experiment works, then you make the real model. It saves a lot of time. A close analogy, not exact but a close analogy, is you have a crystal in real world. Okay, so what you do is, instead of solving problems of diffraction using the real world crystal, you map the structure of the crystal from real world to a reciprocal world. In real world, you use the vectors a1, a2 and a3 to span the crystal. In reciprocal space, you use the vectors b1, b2 and b3 to scan its reciprocal crystal, and then you do the mathematics in the reciprocal crystal. You do all types, you find all the properties in the reciprocal crystal, and whatever answer you get, then you transfer it from reciprocal to real crystal. Okay, so it is just an idea of making a different methodology of doing the same thing. So question is, why do we go from real crystal to reciprocal crystal? What was so convenient? See, whenever we do something, it means we found a convenience somewhere. Okay, so there must be something very easy in the reciprocal world that was not easy in the real crystal world. Because of this, we invented the reciprocal lattice vector. Agreed. So question is, what was so easy in the reciprocal lattice? Now, what calculations were so easy in the reciprocal world that we preferred using the reciprocal lattice of a real lattice? I mean, take a real lattice crystal and look at the structure, and you look at the structure of the crystal and you say that this crystal is spanned by three lattice vector a1, a2, a3. Then you take it to the reciprocal world and you use b1, b2, b3, and you span the entire crystal in the reciprocal world. So the crystal in the reciprocal world is like just the mirror image of the crystal of the real world, and you do the calculation in the reciprocal world. So we'll discuss it in the next lecture, what is so convenient. I hope you get an idea why reciprocal lattice. I hope you get an idea. So some more discussions are left. I need to continue. um, you can use the formula, take it as an exercise. I was planning to solve, but take it as an exercise. Okay, so what you need to do is, given real world vectors a1, a2, a3, okay, you can use this formula here, that is how a1, b1 are related and all these a's and b's are related, and you can find the reciprocal vector, and you can find the reciprocal vector. Similarly, this was for simple cubic. Similarly, for fcc, you are given a real world a1, a2 and a3. You can use the same formula that I mentioned in the other page. So for example, this formula, okay, use this formula, and then you find the reciprocal vector, and you find that the reciprocal vector is this. All you need to do is work with dot product and cross product. It's very easy, not that difficult. Agreed. So this is the idea. In the next lecture we will discuss more about the reciprocal lattice and the Miller indices and diffraction experiments. And in the next lecture you will get a clear idea that why we went from the real world crystal lattice calculations to a reciprocal world and did the calculation in reciprocal space. So these are the b1, b2, b3 are the reciprocal vectors. We'll discuss in the next lecture.